In this example, you're looking at a sort of proof again, and we're going to link this to the ideas of linearly independent and dependent vectors. Remember that two vectors are linearly dependent if, let's put this here, two vectors are linearly dependent if they are parallel. Oops. So we can see, and we're going to see that as we progress through here, that a couple of those vectors that we look at are parallel, and hence they are dependent on one another. So the first thing we've got here is points A and B have position vectors A and B respectively relative to the origin O. So O is here. We've got A and B as the points, and we've got two vectors. So I'm just going to do these in colours so we can see them. So we've got A is the vector from O to A. I'll do that in green. So this is OA, that's the green vector, and then in purple, B is the vector from O to B. Okay, so we've got a couple of things labelled on our diagram. Okay, something else that may be useful here would be this other side as well. We'll get to that. Now it says the point D, which is here, is such that OD equals KOA. Now this expression here, OD equals KOA, so O to D equals KO to A, where K is some real number, means that OD is parallel to OA. And you can see in the picture here that OD is a fraction of the size of OA. So it's in the same direction, but it's a fraction of that. Okay, so we could also express here, we know that OD is a fraction of O to A. We know what O to A is. O to A is written as A. So we also know then that this expression, OD, equals K times OA, which is A. So KA. So we know that that part there is KA. Okay. The other thing that we know, the next part of the question, and my idea with these questions is always write down what you know as you're reading. So the next thing it says is the point E, so that was point D. The point E is such that AE equals LAB. Now AB we actually can express in terms of A and B only. So if we have a look, and I'll do this in another colour, we've got A and B. So let's go from A to B. Oops. From there, in yellow. If we think about what A to B is, you'd be starting here at A going to O, so that's backwards the green vector here. So it'd be actually going backwards A, so it'd be negative A. And then we'd be going the positive way up the purple vector, which is B. So we can label these, and I'll label these on the diagram. I might do them in black. So you've got B, you've got this yellow vector, which is negative A plus B, and you've got the green vector, which is A. We've also got here the little vector OD, which again we know, and I'll do that in a little black, is KA. Okay, I'll just do that. And the next part here, we've got the point E is such that A to E is L times AB. So A to E, I'm going to put that in here as well so we can see it. There's A to E. And if we think about what that means, A to E equals L times A to B. L is a scalar, so again, this means that AE is parallel to AB, and that implies that AE equals, we know already what A to B is, we figured that was negative A plus B, so A to E would be L times negative A plus B. Or if you want, you could write this as B, take away A, it's the same thing. Okay, so we've now got expressions for all the different vectors that we've labelled here. Okay, the last part here, it says the line segments B to D, so this one, and O to E, which is this one, intersect at X. If O to X is given by this expression and X to B is given by this expression, find the following. Now O to X here is saying that O to X is a scalar multiple, 2/5, is a scalar, that's a real number, okay, of OE. And we also know that XB, so this one, okay, is a scalar multiple, or DB is a scalar multiple of XB. So that means that in each one of these sets, these are all parallel vectors as well. Okay, so we're going to use the information that we know to try and express a few different things here. So the first thing we're going to look at is O to X, and we're asked to find O to X in terms of A, B, K and L. Now we have some expressions for K and L, and they have A and B in them. Okay, so let's look at what we're asked for here. It's O to X in terms of A, B, K and L. So we've got an expression here, and I'll just write that down. We've already got an expression for OX in terms of OE. So we know OX is 2/5 of O to E. So let's have a look at O to E. I'll just draw a red line there for that. This is O to E here. So if we want to express O to E in terms of what we know, we could do that a number of ways. The easiest way is probably to go along the green one and then up along the black one there. Okay, so we know already that that black vector, A to E, was given by this expression here. It doesn't really fit very well. I'll just sort of draw an arrow there. So that's the expression there. So we're going to have O to X is 2/5 of, and it's easiest for us to go O to A plus A to E because they're actually both oriented in the correct way. So we've got O to A, which we know is just given by A from our picture and from here, and then A to E we know is given by this expression L minus A plus B. So if we wanted to expand that out, and I'll just copy that to the next part. This is OX that we're writing here. So we've got 2/5 of A minus LA plus LB. And you might want to factor it so that you've got the A all together. So you've got A outside of 1 minus L, and then you've got LB like that. So this is sort of just a neat way of doing it, and that's OX. So you can see that the question was asking us express OX in terms of A, B, K and L, and you've expressed OX in terms of A, B and L. There's no K here because it's not relevant to the question. So we've done that one. The next one is XB, and we've got this expression here for XB, in blue. So XB, let's get rid of that there, is going to be found in a very similar way. Just putting that back again. So we've got XB, which is going from here to here this time. And we know that XB is given as 4/5 of dB. So let's write it out. So XB equals 4/5 of dB. XB equals 4/5 of dB. Now if we look back at the diagram here, if we wanted dB, and I'll do this in, what have I got? Light blue. D to B. You can see again that you can construct D to B by using information that we have already. So you could go a couple of ways here, but it's easiest to go this way, I think. So going back along this way and then up. So this would be negative Ka plus B. Okay, so we can do that on the next slide. So D to B is negative Ka plus B. And in terms of the answer for that, there's not really much else that you can do with that that's interesting. I suppose what you might want to do is maybe expand it if you wanted to, but it's nice that it's factorised because you've got the 4/5 outside there. So using the information you already knew, going from D to B and just constructing that from what you have, you've now written X to B using this expression. So you're really using the expressions they give you. You've used this expression here to give XB in terms of A and B only. There's actually no L and K involved in this one. The last part, part C, we're asked to find K and L. Now we already have a couple of expressions that have K and L in them. In particular, we've got the expression for OX that has L in it, and the expression for XB that has K in it. Now unfortunately you can't really link those two together very easily. So at this point it's a good idea to re-express either one of XB or OX in a way that introduces maybe an L or a K, so that you've got two things to work with. So you'd have two expressions. And in this example, it's actually easier to work with XB. They'll both work though. So we know already that we could express XB as a fraction of dB, and we knew what dB was from our work on that picture. Now XB, if we identify that, this is XB here, it could also be expressed going along this vector here and then going back up here. And what that would equate to is going along this vector XO, okay, and then up OB. So I'm just going to write here for C, this is an alternate XB. XB can also be expressed. So we'd have XB equals XO plus OB. Now XO is something we don't have. We do have OX though, and OX is the backwards of this. So what we could say here is it's also equal to the reverse of OX plus OB. Okay, that's because OX would be going that way, and we want to go that way against OX. So it's the negative of that. And we know that O to B is B, and we know what O to X is. We actually found that already. So we've got negative what we found OX to be, which is over here, A 1 minus L plus LB, and then we know that OB is B from the diagram. So you could expand that out as well. So I'm just going to keep it 1 minus L, that's all the A stuff together, and then here with the B's, I'm just going to keep the B's, this would be, actually I might do it sort of more formally, so negative 2/5 LB plus B. I'm just going to factorise it so that the B's are all together there. So plus B, and inside there I'd have 1 minus 2/5 of L. I'm just factorising everything that's there. So that's XB. So now that we've got two expressions, since XB is also this expression, which we found in part B, we can equate those expressions, or equations. So expressions for XB. Now the reason that we can do that is that A and B, those two vectors, they are independent vectors. Why are they independent? Because they are not parallel. So they're linearly independent vectors. What that means is it's like thinking about X and Y. You know, X and Y are independent as well if you think about they're perpendicular to one another. So you can write things in terms of X and Y and then just equate the coefficients of X and Y. It's the same thing here. If you have linearly independent components, A and B, so since A and B are linearly, let's go to the next page, independent, you can just equate the coefficients of A and B, because that means that there is a unique expression for that vector XB. So we're going to do that now to finish off, to try and find K and L, and you know you'll be able to because you've got expressions here that have K and that have L. So I'm just going to copy these over so we can see them. Two expressions. They're the two expressions we have. Oops. And we'll get started. Alright, so when we make each of these equal each other, we now have this top line, so negative 1/5, okay, of, oops, I need to be careful here, that should be a 2. Thought that looked funny. So we've got negative 2/5 of 1 minus L A plus B, and we've got 1 minus 2/5 of L equals, so that's XB, and we let that equal this other part here, 4/5 of negative KA plus B. Now, because in the form it is here, it's not very useful to us, I'm going to expand so that left side is going to stay the same, because that's already split up into A's and B's. And at this point too, once we split this up, I'm just going to expand that right side, you've got negative Ka of that 4/5 plus 4/5 of B. You could use your calculator here to solve. So we've got, for A, we've got negative 2/5 of 1 minus L equals negative K 4/5, or negative 4/5 of K. Okay, and for B, equating the coefficients of B, we've got 1 minus 2/5 of L equals 4/5. This one's going to be the easier one to find L. Okay, so we have, I'll just take this over to this side and this to this side, so we're sort of dealing with positive numbers. So 1 minus 4/5 equals 2/5 of L. 1 is 5 over 5, so this will leave you with 1/5 equals 2/5 of L. And when you take this 2/5 over to the other side, it will become a multiply and it will flip over. So we then can cancel and we end up with L equals 1/2. So we found the value for L, and because of the way that we've done this, that L will satisfy both of these expressions for xb, so it's consistent. And now that we've got L, we can simply substitute that L into our other expression here to try and find what K is. So I'm just going to take that one, and as the last step, we'll put that on this page. And we have, since L equals 1/2, we have negative 2/5 of 1 minus 1/2 equals negative K, and that's 4/5 of that. So again, we've got here, this is going to be 1/2, so negative 2/5 times 1/2 equals negative 4/5 of K. This is going to be cancelling, so we've got negative 1/5 equals negative 4/5. I'm going to take all of this, actually both sides, if we divide both sides by -1, makes everything positive. It's always a good idea to do that when you're working. And we'll also divide both sides here by 4/5. What that's going to do when you take the 4/5 to the other side, it'll flip over and it will become a multiply. So you're going to have 1/4 for K. Okay, so what you've done is you've actually found expressions now, or values for K and for L, and the way that we did that was by finding two equivalent expressions for a particular vector that we had in our diagram. That diagram here, finding two expressions for x to b. Okay, the first one was given to us, it's a fraction of dB, and we expressed dB in terms of what we knew, and we also expressed x to b by using other vectors that we had there. Because we knew a and b were independent vectors, we could then equate the coefficients of a and b to get two expressions to help us find L and K. So for this question, for part C, the last part, L is equal to 1/2 and K is equal to 1/4.